Okay, good afternoon. Apologies for the delay in the start of the lecture. We now move to a new topic. Let me just log in. In the meanwhile, while this thing is starting up, let's speak about your project. Your project is to be done. Your demo is on Friday. Anyone who wants to demo in advance can do so this afternoon at 5 o'clock. Right? Already, some students they had some personal issues. One or two of them were sick. A few of them. I think they wanted to get it out of the way because of the test or something, or project. They wanted to leave Friday free. Okay, anyway, whatever the reason was, few of them have demoed to me already. Right? They emailed me, they made an appointment to come and see me, and their project was working. It was very, very pleasing to see that the project was working. So just a show of hands, how many of you guys like 3/4 way into your project, like trying to fix the simulation now? How many of you, anybody working? Anyone working? Yeah, you can, if it's working, you just come and demo it this afternoon, so you don't have to come in on Friday. All right. Also makes it easy for me as well, because that means I don't need to mark you on Friday. If I mark you today, that's it, you're done. Then all you do is you just submit your report, which is due. When is the report due? Anyone got an idea? Hang on, let's check it out. Let's check it out. All right. Okay, all right. Let's just check out our due date. When is our due date, guys? So the report, according to our rules, is due. The demo is on Friday. That's just the demo. 10th May. That's day after tomorrow. Report deadline. I haven't given report deadline, right? You want the report due next week or something like that? Okay, all right. So demo we'll still have on Friday. A demo is 70 out of 100 marks. Okay, if your project is 100 marks, 70 out of 100 is the demo, right? And obviously, to do the demo, it means you've done your calculations. At least you have your hand written state table ready and your handwritten K-map ready when I come around. I won't mark the K-map. If your demo is working, straight away I'll know your K-map is okay. All right? Okay. And the report, you can, I can make it due on Monday or Tuesday or something like that. There's no labs next week. That's the good news. No labs next week. All right? But I need to mark your report as well, so that that comes part of your final mark for your project. Circuit file submission. Over here, one of the students was asking me, "Hey, what is the code file?" Code file. That means the circuit file, eh? The circuit file. When you do your project, you've got you made your maybe the circuit maker file, right? The CKT file or Logicm. I don't know what's the code. And you basically upload it over here so that I can check it later on, right? I can check it later on as well. All right, and your project report. So I'll delay the project report. I can do that so that until next week, Monday. When do you want it? When would you like it? But we don't want it to be too much next week, because then your short test will be affected, and we want to have your short test sometimes next week. Maybe over here, right? Or maybe maybe over here. Then we leave the last lecture for wrapping up any minor thing which is left over. All right, so we have today's lecture, tomorrow's lecture, next week Monday's lecture, and next week Thursday's lecture. Wednesday's lecture we'll leave it for the short test number 2. All right? Okay. Any questions, guys, with regards to the project? How many of you, anyone working? Anyone working? 1, 2, yeah, you can come and demo this afternoon if you're ready, right, at 5 p.m. Unless you got a lecture or something. What's at 5 p.m. apart from the 222 lab? Anyone else got something? No? Okay. All right. Okay. Guys, what I want to introduce you to is, and this note is not fully over yet. I was just scanning it from a book because I don't like to generally reinvent the wheel. I like to use things which are already available, right? But for certain explanations, we have to you know, obviously write things down because we want to show the calculations. All right. Whatever this note was. Synchronous. Okay. It says week 13, eh? All right. Guys, I want you to. Where did week 13 notes go? Week 13, and what about week 11 notes then? Okay. Is this the same note? Okay, so the same note shows up in week 13 and 14 as well as. Is that correct? Okay. All right. And over here, sequential circuits. All right, guys, I want you to make an observation for me. What can you tell me about the clock line in this particular example? What can you tell me about the clock line? The clocks are all tied together. So all the flip-flops, when you trigger, remember, now that you're doing the project, now it's starting to make sense why we use the word trigger. We use the word trigger. You probably noticed that what do you call, if you're using Logisim, you click on the clock button. If you're using Circuit Maker, what is it? How many are using Circuit Maker over here? Anybody using Circuit Maker? That's also easy. All you got to do is you just have a push button over there, and you just press the push button that sends a clock signal, a clock pulse, right? So triggering, when you one up and then low pulse of a clock, one complete cycle of a clock, one clock pulse triggers the flip-flop. What does it do? Triggers the flip-flop. What does triggering mean? It makes it change state. And what does it change state to? According to what is being fed over here. What is being fed into the inputs and what the current state is. Yeah? Okay, and you already know the excitation, right? What the current state is, right? Oh, the characteristic table. The current state together with the current flip-flop input, this results in the changeover to the next state. And the changeover happens upon the clock triggering. So you see the clocks are tied. Let's look at the next example, going up. Another one here. We did this in class, is that correct? Did we do this one in class, this particular example? All right. Okay, there we go. Okay, the clocks are all tied together. So what does that mean? Implicitly, it means that all the flip-flops, they trigger together, all triggering at the same time. All triggering at the same time. Okay. Now, there's something else called the timing diagram. Nothing too difficult about the timing diagram, right? All you got to do is, when the clock triggers, if it's a negative edge or positive edge, there's a particular edge. What do we mean by edge? Let's have a look at it. Okay. Over here, can you see there's a bubble in front of the clock? That triangle over there indicates a clock. If there's a bubble, that means it's a negative clock. It's a negative clock. With negative clock means what? Negative edge means falling edge. When the clock was falling. See, the clock goes up, rising edge. Did you guys, at some point in time, did you study this about clocks? Rising edge and falling edge? Okay, let's do that today. All right. So, whenever you have a square pulse, whether it's this one, this one, this one, or this one, whichever one, right? There's something known as rising edge. Rising edge is when it goes from low to high. That's the rising edge. That's the rising edge. That's the rising edge. Rising edge. Rising edge. Can you see it's going from low to high? That's the rising edge. Now, whenever clock goes from high to low, that's the falling edge. Doesn't have to be the clock, or you could say the falling edge of signal X. It's there and there, right? Okay. Whenever the signal goes from high to low, you're going from higher ground to lower ground, that's falling. Yeah? So falling edge. The words make sense themselves. Rising edge and falling edge. Now, at what point in time is the clock being triggered? At what point in time is the clock being triggered? Sorry. At what point in time, not the clock, at what point in time is the flip-flop being triggered? Do we take it, because it's got to trigger. Trigger means at the point in time it takes in new information. Change, change, change. The clock pulse consists of a low and then a high. One complete clock pulse. When you use the word pulse, there's two things. One is the clock signal. The clock signal is this entire thing over here. Yeah? The entire signal. Right? They call that the clock pulse train. Right? You may want to make some write down some of these words, right? I don't think it's in the note. The clock pulse train, or they call it the square wave, the clock wave, right? It looks like a square wave. But if you use the word pulse, it means only one portion, only one low and one high, or one high and one low, right? Okay, now, at what point in time does the circuit trigger? At what point in time does the circuit trigger? Let me do some more of this over here. So that is determined by what's sitting in front of the clock. If there is a bubble sitting in front of the clock, that means that's a negative edge, a falling edge. Can you see the bubble? The bubble indicates that that's a falling edge. The click flip-flop will trigger upon the falling edge of the clock pulse. If there is no bubble, generally there is a bubble. Generally we use the bubble one, right? If there is no bubble, that means we are using the rising edge of the clock pulse. So let's have a look at the timing diagrams. There we go. Okay, I think we did this one in class, right? Yeah, so that's a negative edge. And if you go up earlier, this CLR is clear, which means just to reset everything up. Okay. Most of our flip-flops are, we design them to falling edge. But hey, there's no big deal. You can always make it rising edge as well. Okay, can you see trailing edge? Oh, another terminology used is, instead of falling edge, we call it trailing edge. Trailing edge. Yeah? Trailing edge triggered. Trailing is falling. Yeah? Okay, and leading, can you see there's no bubble over here? That's a rising edge. So sometimes you'll see some textbook, because I know you guys might be doing some internet research, looking at YouTube problems. That's okay, that's all good. We want to encourage you. Remember, only 10% of the knowledge which you will use in the industry comes from your lecture room, right? Most of the knowledge will come from, you will be thrown into, because I don't know how many of you will, maybe only out of your lot, out of the 100 students doing 222, let's say 50 graduate at the end of 4 years, right? Maybe 2 or 3 might end up dealing with traffic lights or something. And even then, they might not be doing design based on flip-flop. They might be using something called PLCs, programmable logic controllers, or they might be using some high-end $10,000 software which only deals with only traffic lights. Yeah? But how will you learn that? You say, hey, my 222 course or my lecturer didn't teach us this software. No, you have to learn on the job. And how do you learn on the job? Basically, you'll be doing research. You'll look on the internet, you'll find some help file, you look at some YouTube videos, you read through some forums. I think if in terms of knowledge for solving engineering type problems, it's the forums. I don't know if you ever read through any of those forums. It's the forums where the solutions are. YouTube videos, they're the good starting point. If you, let's say, you are totally lost, you don't know what Imran is saying when he's saying JK flip-flop. Totally lost. For that, you go to YouTube. That's introductory level. For advanced level stuff, like if you've got a problem in your circuit maker or something, you go and read forums. There will be other students, other people who have tackled the same problem, and then somebody else is commenting, no, don't go that route, you go this way. How many of you have read a forum, internet forum? You will see. But the problem with internet forum as compared to YouTube video or any other video, YouTube video, you just sit down, you watch, you press pause, you note down, you continue, and accept. You know it already. Problem with forums is you have to read, search, and they might give a link, you go there, you have to dig. It's more like mining. You have to mine. So for example, I'll give you a real life example. I had a problem with my car. It used to make, not the Prius, I used to have a Nissan. And it used to make this sound called the pinging sound. And sometimes some people call it detonation. Some people, some engineers, depending on where you're based, different people use different words for the same thing. That's another terminology. So that's why trailing edge, leading edge, rising edge, falling edge, right? So, some people might be calling it going up, going down edge, you know, right? Okay. And sometimes some terminologies, they go, trailing edge is H-L, high to low. And leading edge is L-H, low to high. Yeah? Okay. And I took it to a couple of mechanics. And the mechanics were, they didn't know quite exactly what they were talking about. It was a problem to do with, not a big deal. It wasn't a big problem, I knew, because the car was still working. It was only making sound when your engine revolutions is between 1000 and 1600. So between this range, 1000 and 1600, the engine was making sound. So we took it to the first engine, first mechanic, and the mechanic said, oh, the solution is, oh, this is a funny one. He said, don't go and fill fuel anywhere else, only fill mobile fuel. And I knew the source of the mobile fuel and Pacific Energy is the same source. Which means when those fuel tankers go, they fill up from the same refinery in Singapore. So it's the same source, it's only branded here differently. Same fuel. You can taste it, you'll taste the same. Yeah, right? Okay, right? Okay. Now, then I took it to the next guy, and the next mechanic said, "Boy, your engine is almost about to give up. You sell me the car and for $2,000 or something really low." And I mean, the car was not really that old. It was about 4 years old. I had bought it second hand, but it was like a 2006 model. So I knew the value would be around about 10, 11,000. They sell me the car for $3,000, and at least I can fix it. I can change the engine. The engine has to be changed. But if you do it, you'll go in a loss. So extremities, you know, extremities. Never take extreme solutions. Always the solution is middle. And then I started researching, even though I'm an electrical engineer, more so I'm an electronics engineer. Right? I started researching, and then eventually I found on the forums, looked through the YouTube videos, and most of the videos with that particular car, it was a Nissan Wing Road. It was a station wagon. Looks like a Nissan Tida, but station wagon. Eh? And most of those sort of cars were being used in Russia. So most of the videos were in Russian. So couldn't understand, but at least you can see they're doing something, you know. But their language you couldn't understand. Sometimes some of those videos you can translate on YouTube. You can translate other languages. So from those videos I picked up something. They were continually referring to the EGR. Then I researched the EGR. I found some forums. And then on the forums it was, yes, that this particular valve, the EGR, is the exhaust recirculation valve. And that gets clogged up with carbon. So then we just took it to one of the other normal mechanics, not to those two guys. Took it to another mechanic. We opened the valve up. We cleaned the valve was blocked. You know, there's this carbon cleaner. Sprayed it, cleaned out flushed out all the carbon, put that back in, and then now, when I turned on the car is revving higher. It's higher. It's revving at 3,000. So that's another problem. So again, we researched on the internet. found that you have to reset your computer board. How do you reset it? You either get the onboard diagnostic kit and then do some kind of programming over there, or if you've got this particular model of Nissan, you press the brake pedal once, then lift it, then press it again twice, like a Morse code, 1010111001, and then press the thing valve, and then press this button here, and did that, and then it worked, and then that particular pinging noise that disappeared. So a lot of the information which you will find when you are in industry, this advice is more so for the industry. You'll find it on the internet. Introductory knowledge will always be on YouTube. YouTube will have some 1 or 2 hints, right? If you watch through the entire video, and sometimes the language won't be right, so you'll have to pick up on certain things which they are mentioning, right? Because certain terminology will still be the same. So for example, flip-flop in Russian will be the same word they use. SR flip-flop will still be called SR flip-flop in English as well as Russian or Arabic or whatever, right? From there, you'll find some terminology which they're using to fix that particular problem. Then you search that terminology and you might find it in a forum. And then when you read through the forum, there's other people who've been trying to crack the same problem. You're probably not the only person who's cracking the same problem, right? Sometimes that problem is being cracked on some other car. So the video I found was they were trying to solve this problem on a Mazda, but it was the same problem. And generally, you'll be able to do the same. So that's just like how, let's say if there was a clock pulse, if you got to do it in Logisim, there's one way, and not much difference to do it in Circuit Maker, right? Okay, but so long as you get the concept, you can then transfer your knowledge, and that's what will happen. So it's very important for you as a skill, as an engineer, to be able to find the information which somebody else has done, and then pull it and modify it. You can't just copy and paste. You can't go and use the Circuit Maker information and directly try and upload that file onto Logisim. It won't work, right? You've got to modify it, okay? Modify it to suit your particular circumstances. Then it will work. So over here you've got leading edge and trailing edge. Some people call it rising edge and falling edge. Now let's come back down here. So the main point I want to make over here is that you've got something called a timing diagram. Now the timing diagram starts to become important, all right? And you will see that the particular, can you see the falling edge, that's where, and soon after the falling edge, just a micro, we show it deliberately, we show slightly later, right? But for the purpose of examination, we can do it later as well, right? We show that, hey, this thing here is the point at which that line there, can you see the dotted line? 1 millisecond later, because it takes some time, right? There's some processing time. That's why in your memory, if you get your flash disk or if you get an SD card to fit in your mobile phone, they usually, if you buy the brand new packet, it says how many megabits per second, the SD card speed. Have you seen this or not? Right, when you buy an SD card for your mobile phone or for your camera, nowadays nobody uses the camera, it's all on the mobile phone. Or if you buy an SD card for your laptop, right? It gives you the speed of the memory. The speed is the time it takes for the flip-flop to trigger. So that's why, realistically, if you look at the clock signal, can you see there's a small increment there, right? Which indicates there's a slight delay, right? But generally, it changes. Now you'll say, hey, D went high because D is being set by the user. D is being set. D is the input into the flip-flop. Is being set by the user. Then, at this point in time, at this falling edge, D was considered to be 0. See, right? And then from there on, every falling edge, they look at what the D is at that intercept, and then they change Q and Q bar accordingly. Obviously, Q and Q bar will always be opposites of each other. In the very first scenario, Q and Q bar is unknown. That's why we put like a block. It's could be 0, could be 1 in the very first circumstance, and based on D, right? Those things change accordingly, right? So this is a timing diagram situation. That's D, so clock and D. This is the timing diagram. Clear and preset, basically that's clearing the flip-flop, flushing it out, but the main lines for you to learn is this one here. Clock, D, Q and Q bar, clock and D. They've got the SR flip-flop over here. Now, they've got the T flip-flop over here as well. If you look at it, if you look at the diagram, I didn't show you the diagram. Let's go to the problem of our analysis over here. What sort of thing is this? Is this leading edge or lagging edge? Is this trailing edge or falling edge? I mean, rising edge or falling edge? That's a falling edge triggered system. The system is triggered by the falling edge. So when you look at our timing diagram, this one here, what about this one here, guys? That's a falling edge. Mostly we'll find falling edges, right? Now, can you see what's happening over here? So basically, all we're doing over here in this timing diagram is just following just another way of drawing our state diagram. Another way of drawing our state diagram. So if x is this, right, at this point in time, at this falling edge, x is considered to be 0. The status of flip-flop A is 1. Status of flip-flop B is 1. Status of output Z is 1. And then based on the new calculations, what happens, right? So it's all we are doing is redrawing in more like a timeline type of situation what our particular inputs and outputs are. And of course, you can't draw this without drawing the state table. All right? Okay? This is more like the state table. Okay. So there we go. That's a JK and D system. All right? Something similar. Some of you may have received something like that, but except for you may have JKD, JKD, right? Or something like that for your project. All right. Now, the key observation. Let's come back to our original discussion. The key observation was that your clocks are all tied together. So they are all synchronized. Now, let's show you a new type of circuit. And this is also available in this one here. Now, what observation can you tell me about your clock? Look at where the clock is being fed from. Where is the clock for the second one coming from? It's coming from the output or the Q of flip-flop 1. Flip-flop 1 is feeding the clock into flip-flop 2, right? Flip-flop 2 is feeding the clock into flip-flop 3, right? This is what you call an asynchronous system. It's called an asynchronous system, asynchronous counter. All right? Okay? Now let's go through the theory of this. Let's go through the theory. And what I've done is, deliberately, because can be confusing, I have loaded onto your particular thing something called the asynchronous counters, right? So that's a 4-bit counter, and we use deliberately something called the JK flip-flop, our JK flip-flop. Now, what's so special about a JK flip-flop? What's so special about a JK flip-flop? Over here, they use the T flip-flop. So you can either use the JK flip-flop or you can use the T flip-flop. Now, what happens in the T flip-flop or the JK flip-flop? Can you tell me? What is so special about the T flip-flop? Oh, JK, let's discuss JK. Let's stick to JK. Let's come and maybe look over here at this circuit. So can you see the circuit? The clocks are not synchronized. You know, if it's a synchronous counter, the clocks will be synchronized. If it's asynchronous, the clocks are not synchronized. Let's look at this one here. Uses JK. Right. What can you tell me about this circuit here? If for just let's look at number 1, the first one. This guy here. This is a scan from a textbook, all right? So only 4 pages, so it's easy and it's very explained in very simple terms. All right. Now, and that's on Moodle already, eh? That's on Moodle already. Okay. Now tell me, what can you tell me about the first flip-flop? Both J and K are 1. That's the first hint. What do you think will Q be? Of course, there is a normal clock pulse which is being fed into our first one. Yeah? The normal clock pulse is being fed. The difference between this counter and our earlier counters was that the clock pulse would have been all synchronized. Over here, it is not synchronized. Only the first flip-flop is receiving the clock. Now, what can you tell me? This is 1, this is 1. Now, remember the theory of JK. What does JK do? If both are 1. In SR, if both are 1, what happens? Flips out, right? There's no flip-flopping then. It's invalid. Yeah? For SR, it's just invalid. Right? You can't, there's like a no-go zone. Not used. Right? Strictly not allowed. Not allowed, not used, invalid. Right? So that's why we move away from SR in asynchronous. Asynchronous, we want to use either JK and T flip-flop. Because in JK, what happens? It can use it now. Remember I showed you the theory. I did a step-by-step explanation of JK. So what happens in JK? Go on, tell me. What happens to Q? It toggles. Toggles. So if one round it shows a 1, the other round it will show a 0. So remember the normal clock pulse, this guy here, this fella here, sorry, the top guy. The normal clock pulse, high, low, like a square wave, like a square wave. A wave is something which is periodic, going up and down, but consistent time on, consistent time off. That clock pulse is being fed into here, the one on the left, all right. So if a normal clock pulse is being fed in, these two are 1, what is happening to Q? First round, on the first trigger, oh, what is it? Falling edge or rising edge? Rising edge or falling edge? Look at this bubble here. Falling edge. So because this is 1, 1, on the falling edge of the original clock pulse, which I just showed somewhere down there, right? This thing will become, let's say 1. We assume something, right? Remember, we assume. Then on the next falling edge, it will become 0. Then 1, 0. What happens over here? That means this itself is now starting to look like a 1, 0, 1, 0, 1, 0. That itself is starting to look like a clock pulse. Except for, what can you tell me about the frequency of this output compared to the frequency of this? Has been halved. Halved. This here, okay, let's now have a look at it. And then that 1010 is being fed into this clock pulse. Yeah? Okay? And then what happens here? This 2 is 11. That will also toggle on the what? On the falling edge. So it takes 2 clock pulses. Remember, for one falling edge, how many pulses does it take? 1 clock pulse, right? So 1 clock pulse, this becomes 1. Another clock pulses, this becomes 0. So for 2 clock pulses here, you achieve 1 clock pulse here. Alright? Again, for 2 clock pulses here, you achieve 1 clock pulse here. For 2 clock pulses here, you achieve 1 clock pulse here. For 2 clock pulses here, you achieve 1 clock pulse here. Alright? Okay? So that means 8 over here will result 4 in this output here. 4 over here will result 3, 2 here, 2 will result 1, and so forth. Can you see it goes downwards? Now, have a look at the timing diagram. There we go. Alright? Now that's an asynchronous counter. Another name given to this particular counter is, it's called a ripple counter. A ripple counter. How many of you played or seen maybe a video on YouTube or internet, whatever you watch, dominoes? We played this thing called dominoes. You know, it's like little blocks, very thin, but it's a block. It can stand on its own, and then you place another block beside it, another block beside it, another block, and you leave, let's say, 1 centimeter gap or 1.5 centimeter gap, and then you make a long line, and then you trigger this one, the first one, and then all of them start to ripple, right? Right? they start to fall in a line, right? That's called a ripple. Yeah. So what's happening here is the way this thing is structured. It's called it is working in the form of a ripple counter, which means in order for the second flip-flop to get trigger, the first trigger has to trigger, right? And the third one, the second is to trigger. For the fourth one, the third is to trigger, all right? So it's a ripple system, rippling system. So another word is ripple counter. Another word is asynchronous counter, right? Asynchronous counter or ripple counter. Now, I'm going to give you a few minutes to just go through that. I'm going to give you a chance to look at this diagram. Let me make it full. How do I make it full? All right. Okay. Oh, can't zoom in. I can't zoom in. Okay. View. Full screen. That one. Now. Okay, just maybe make it slightly smaller. Right. There we go. There we go, guys. I want you to take note of this. This is discussed with your partner. This is the important part. This is also examinable in your final exam. There will be maybe 15 marks on asynchronous counters as well. All right. But the good news about asynchronous counters is that there's not much calculations to do because you've already done the hard calculations for your project. All right. Okay. Now, have a look at this. All right. I want you to follow through what's happening. Compare our clock pulse to this. Now, the other thing I wanted to mention is that the word modulo. The word modulo, right? Modulo means the level till which it counts. So if you say modulo 16 counter, it means it counts till the number 15. If it's a modulo 10 counter, it counts from 0 to 9. Right? Now, you may be wondering, why is Imran always talking about counters? Once you get counter, you can build a timer. Once you build a counter, you can build a timer for your. So, for example, if you wanted a 10-second counter, like the light to go on after 10 seconds, and your clock frequency over here is let's say 1 hertz. 1 hertz. So you want the light to go on after 10 seconds. What do? You build a modulo 10 counter, right? Or whether you want to build synchronous or asynchronous, right? All right, and I'll tell you a bit about that later, right? Whether you want to build asynchronous or synchronous to get approximately 10 seconds, right? And you feed your clock pulse to be 1 hertz, right? The moment it reaches 10, the output should become 1, just like what we did in our last lectures. But the only difference is now we are looking at asynchronous. The word modulo, remember that, note that down. That's going to come in the exam. Modulo, spell modulo, all right? Okay. Yeah, no, spelling won't come in your exam. Right? Okay. Right. Okay. Right. Let me just show you over here. Yeah, modulo 16 counter. The modulus of the counter is the number of counts it goes through. So please read through these notes and we'll continue them later on. So right now what we are doing is we are trying to focus and see how this diagram is related to that. That's flip-flop 1. I think that's where the mistake is in this note. The flip-flops are not numbered accordingly. This should be called, oh yeah, it is flip-flop 1, flip-flop 2, 3, 4. Okay, so can you see the cue, right? Now I want you to notice, I'm not sure if it's observable from where you are sitting down. Can you see the falling edge? The change in state is slightly after. Now, a quick question, and we've got only 2-3 minutes to go. So sorry, this was a shorter lecture. I think I started a bit late. If you were to compare synchronous and asynchronous, which one would form a better timing system? How many people say synchronous? Let's do voting. And how many people say, okay, let's start off with synchronous and asynchronous. How many people say synchronous is more accurate? Hands up, man. 1, 2, 3, 4, 5, 6. Okay. How many people say asynchronous? Okay, 2, 3. All right. Okay. It's okay. It's just voting. We won't win any election or anything. Right.